Okay, today we're going to continue talking about steady state one-dimensional problems. We're just going to add kind of a twist, which is this idea of thermal energy generation. So thermal energy generation is sort of a concept that ought to initially give you a little bit of a pause if you've taken thermodynamics, because in thermodynamics, one of the basic premises, one of the things we did for most of a semester is balance energy. And that energy balance is based on this idea that energy is conserved, energy is never destroyed, and it's never generated, right? So now we're in heat transfer, and we're going to talk about this thing called thermal energy generation. And you have to be a little bit careful to make sure that we understand what this means. So we're not talking here about energy generation, because, again, in this class, energy is always conserved, right? We're talking about this idea that when we do energy balances and heat transfer, a lot of the times what we're doing are energy balances on thermal energy, right? So if we have energy conversion processes where energy from some form is being converted into thermal energy, then that thermal energy could be showing up in our balances as a generation, right? It's not a generation of energy, it's a generation of thermal energy. And that thermal energy is nothing more than a manifestation of energy changing forms, right? So an example that we're all pretty familiar with probably is electrical energy, right? So if you put a current through a resistor, you're putting in electrical energy, and that electrical energy is being turned into thermal energy in the resistor, right? If you have a really bad heating system, that could be the heating system in your house, right? Is electrical resistance heating. So you're then turning electrical energy, which is work, into thermal energy, which is eventually heat, right? So that's going to show up as a generation of thermal energy, but really all it is a degradation of the electrical energy, right? That process is always going to be accompanied by an entropy generation. The problem we're going to work on today is a problem where chemical energy is being turned into thermal energy, right? So basically, an exothermic reaction is the same kind of a deal where you have a reduction in the chemical energy of some kind of material, but that reduction in chemical energy turns into thermal energy, right? So that's an exothermic reaction. You're turning chemical energy into thermal energy. Nuclear energy, same thing, and you could have some kind of an absorbed radiation problem where radiation is being absorbed, for example, in a lens. That lens is going to start to get hot. That's a generation of thermal energy. One thing that you have to get familiar with or comfortable with when we're talking about thermal energy generation is this idea that thermal energy generation is typically a volumetric phenomena. So it's not usually occurring at a surface, right? It's not a boundary condition. Instead, it's actually something that occurs within a surface throughout its volume. So most of the time, you're going to see thermal energy generations specified for you in terms of a volumetric rate of thermal energy generation, right? So G dot triple prime. And this triple prime means per unit volume, right? Just like a double prime means per unit area, a single prime means per unit length, a triple prime means per unit volume. So this this volumetric rate of thermal energy generation is typically given to you in watts per meter cubed, right? It's meaningless until you know the volume of material that is undergoing that process. And then you can multiply that volume by that G dot triple prime number, and you get a watts. That's the actual rate of thermal energy generation, right? All right, so I thought the best way to talk about this would be to actually do a problem. So here's a problem from actually my childhood, or I don't know, slightly older than childhood, I guess, which is hay bales. So if you've ever baled hay, you know that if you bale hay and it's too wet, it actually can get hot, right? It can get hot enough, if you're not careful, that it could start your barn on fire. And so why does that happen? Well, that happens because, freshly cut hay is, undergoing an exothermic reaction, right? It's basically rotting. And so that exothermic reaction manifests itself as a generation of thermal energy, and if you don't let that thermal energy get out, you can actually find that the hay gets really hot. Hay tends to be not a very conductive material, and so a little bit of thermal energy generation at the center of a hay bale can cause a pretty severe temperature rise. So here's a hay bale. This is the hay bale we're gonna analyze. This is one of those big cylindrical bales that you might see if you drive along the road sometimes in the countryside, right? So here's our hay bale. It's a 5-foot radius bale, right? The hay itself is some composite structure that's mostly air, a little bit of plant matter, so it's got a fairly low effective thermal conductivity, right? This is the conductivity of that composite structure is 0.04 watts per meter Kelvin, not too different than air actually, because mostly it is air. And then inside of here we have a volumetric rate of thermal energy generation that's associated with the hay not being completely dead, basically. So it's 2 watts per meter cubed. So that's what's going on inside of our hay bale. That's the part of the problem we're going to model. At the surface of our hay bale, we have wrapped the hay bale in a thin sheet of plastic. So the thickness of the plastic is 0.045 inches. Plastic's not very conductive, 0.15 watts per meter Kelvin. And then the surface of that plastic is exposed to air at 20 degrees Celsius with a heat transfer coefficient of 10 watts per meter squared Kelvin, right? So we're at least initially going to ignore radiation. We'll come back and talk about that at the end. But that's what's going on, and probably, among other things, what I'd be interested in is how hot does the center of this bale get? Because if it gets above about 170 degrees Fahrenheit, I have a problem where the bale could start on fire and smolder, and bad things might happen. So that's our problem. We're going to assume that the problem's at steady state, and we're also going to assume that the bale is sufficiently long that we can model it as being a one-dimensional problem, right? So there's no temperature gradients in the axial direction, so into the page. There's no temperature gradients in the circumferential direction because nothing's changing in that direction in terms of our boundary conditions. The only temperature gradients are in the radial direction, and those are associated with the energy inside of the bale trying to get out by conduction. That's our problem. We're going to solve it analytically. We'll learn, actually starting next time, techniques that would allow us to solve it also numerically. But today let's do it analytically. The steps required to get an analytical solution to this problem are no different than the steps required for some of the earlier problems, right? And the first thing, the most important step, I'd argue, is actually to derive the right differential equation, right? So in order to do that, we have to do a few things, right? And these were laid out pretty carefully last time. The first thing is we have to define a differentially small control volume. So what does a differentially small control volume look like for this situation? So we have temperature gradients in the radial direction, right? So we said then that it has to be differentially small in the radial direction. So here's our shell. There's no temperature gradients in the circumferential direction, so it can extend all the way around the circumferential direction. And there's no temperature gradients into the page, so it can go, as far as you want into the page. So we're going to do this on a per unit length basis. So L is length into the page. We have our control volume set up, so the next thing we're going to do is first law balance on the control volume. So first law says in equals out plus stored. In can be coming across these boundaries. In this particular situation, the only way energy is getting across the boundary is by heat transfer. So I have a heat transfer rate through this inner boundary. So this is Q dot in the R direction at location R. That's what this means. And then over here on this outer surface, I have the heat transfer rate leaving. So this is also Q dot in the R direction. But now I'm in location R plus dr, right? So I'm out here at the outer edge. And then I can't forget about the fact that my control volume includes inside of it a bunch of hay that is undergoing a volumetric rate of generation. So there's going to be another in to my energy balance, and that's the thermal energy that's generated within that control volume, right? So that'll be G dot. And this G dot has units of watts, right? These are all energies, so these all are, I guess, energy rates, so these all have units of watts. This is watts of heat transfer through this surface. This is watts of heat transfer through this surface. This is watts of of thermal energy generation within the control volume, right? So this plus this has to equal that. So N is this plus this has to equal that. So that's my energy balance. I'm going to then do the next step, which is I'll take my term at R plus dr, and I will expand that and take the limit as dr goes to 0. So that basically then lets me write q dot in the radial direction at position R plus dr is equal to q dot in the radial direction at location R plus dq dot dr times dr. Right, so I just make this substitution right here, and these q dots are going to cancel out. The other thing I got to realize is this g dot term, this is not g dot triple prime, right? It's really tempting to just throw that g dot triple prime in there and forget about it. If you do that, you've just made a big mistake. Your problem's going to be completely wrong. This is the rate of energy generation inside of my control volume. So that has to be then g dot triple prime, so that's the rate of energy generation per unit volume, multiplied by what? By the volume of the control volume. So what's the volume of this control volume? Well, it's a differentially small shell, right? So it's going to be the thickness of the shell, which is dr, times 2 pi r. So that's the perimeter of the shell. So 2 pi r times L, which is the length into the page, right? So 2 pi r times L times dr, that has units of volume, so that's good. And it makes sense to me that that would be the volume of this very thin shell. So this volume multiplied by this volumetric rate of energy generation per unit volume is equal to the total rate at which energy is being generated inside of my control volume. So that's what I'll plug in here. So we'll cancel these two guys and we'll make this substitution. And here is my energy balance. This is my differential equation written in terms of energy. I can cancel through the drs and I get this this term right here, this equation right here. So as usual, if you've done these first three steps correctly, you should end up with a differential equation. It's just a differential equation that's written in terms of energy rather than a differential equation that's written in terms of temperature. And actually, it's the differential equation written in terms of energy that's the easiest one to understand, right? I think if I look at this, this ought to make sense to me from a thermodynamic standpoint, right? When we did this before, so we did this, I think, 2 or 3 lectures ago for a cylindrical shell that wasn't undergoing any kind of thermal energy generation. And we found that dq dot dr, so the rate of heat transfer in the r direction, the derivative of that with respect to r was equal to 0. Right? We found that dq dot r dr was equal to 0. And that made total sense. We said that, okay, if nothing's going on, we're not storing energy, we're not generating energy, then it makes a lot of sense that no matter where I am inside of this cylindrical medium, I'm going to have the same rate of conduction, right? And that was our ODE. That's what we then moved forward with in order to generate a temperature distribution. That is not what I have this time, right? This time I have that dq dot dr is not equal to 0. It's equal to this quantity over here. And physically what that says is the rate of conduction in the radial direction isn't constant anymore. It's changing. And why is it changing? Well, it's changing because as I move through this material, more and more energy is being generated, right? That's adding to the rate of conduction, and so my rate of conduction is actually increasing. It's increasing in proportion to how much energy generation is happening. And that makes a lot of sense to me. Every time I add another little cylindrical shell, what am I doing? I'm making this guy bigger than this guy. I'm making dq dot dr increase, right? So this makes sense to me. You know, it has the right units. It does pretty much everything I want it to do. I'm pretty confident that this ODE is right. So the next step then, if I want to go from an ODE written in terms of energy to one written in terms of temperature, is I have to substitute in a rate equation, right? So that's the next thing that I'll do.